Scientific discovery, faster cancer diagnosis, and smarter energy grids run on physical infrastructure. Every AI ambition is strictly bounded by the specific hardware of a server rack and the massive amount of electricity it consumes. To secure this infrastructure, the European Union introduced the Cloud and AI Development Act, or CADA. The mandate sets a specific target, tripling European data center capacity within the next 5 to 7 years. Today, Europe holds approximately 4 to 5% of global cloud computing power. This chart highlights the deficit. The region accounts for 20% of the global economy, yet relies on roughly 5% of the world's compute capacity. The primary physical bottleneck blocking the CADA mandate is the electrical grid. 40% of Europe's electrical grid is more than 40 years old. These legacy systems were not designed to handle the high-density power loads required by generative AI. Modernizing this infrastructure requires an estimated 1.2 trillion euros in investment by 2030, while current grid connection timelines can stretch to 10 years. These constraints mean tripling capacity requires systemic engineering across the entire stack, from network topography to microsilicon design. AI infrastructure is not a monolithic design. Workloads demand two entirely different network topographies based on their specific function. The first topography is training, the process used to teach massive neural networks like large language models. Training requires digesting massive datasets within centralized gigafactories. These facilities span several football fields and require deep integration with massive power draws. They are often located in naturally cool environments to manage the extreme heat of the learning process. The second topography is inference, the real-time application of those trained models in the field. Inference enables agentic AI, autonomous driving networks, and real-time medical imaging. These operations cannot tolerate the latency or the energy cost of transmitting data back and forth to a remote gigafactory. To minimize that latency, inference requires a highly distributed mesh network of smaller facilities. This map shows the necessary distribution. While training is centralized, inference facilities must be placed in a grid every 100 to 500 kilometers across the continent. Placing high-density compute nodes directly into populated, power-constrained regions triggers a localized energy crisis that traditional data center architecture cannot solve. At the rack level of a single inference node, the physical constraints become immediate. AI workloads pack significantly more processing power into a single server rack, creating a spike in power density. Traditional air cooling is physically incapable of managing this new heat density. Hardware is pivoting to direct liquid cooling and geographic solutions, such as using renewable seawater to regulate temperatures. The adoption of liquid cooling allows the facility to function as an active utility asset rather than a passive energy consumer. Bidirectional grid integration allows data centers to push a stabilizing frequency wave back to the local grid. Meanwhile, the liquid cooling loop captures massive amounts of waste heat, routing it directly into district heating systems for nearby university buildings and residential neighborhoods. Building this closed-loop ecosystem requires high-capacity infrastructure capable of handling the continuous energy exchange between the facility and the municipal grid. While facility integration mitigates grid strain, the baseline power draw must be addressed at the microscopic level, the silicon itself. Examining the motherboard and the processing chip reveals a shift in industry engineering. Evaluation metrics have moved toward total cost of ownership, where energy efficiency is the primary driver of value. This shift has exposed a major energy drain, the data movement tax. Processing data is only a fraction of the total power draw. Physically moving that data across hardware consumes massive amounts of energy. Power is wasted transporting packets from memory banks to the processor core, across the physical gap of the motherboard. Advanced memory architectures improve bandwidth at lower power by forcing data to travel a much shorter physical distance to the processor. This data movement problem extends to the macro level. Transmitting every task from a user's device to a remote cloud server wastes immense energy. Dynamic workload distribution prevents this by executing smaller inference tasks directly on the edge device. By condensing memory architecture and processing at the edge, microsilicon engineering slashes the facility's power demand before it ever hits the municipal grid. This engineered stack, microsilicon efficiency, thermal recycling, and distributed networks, must work as a single unit to meet European goals. These engineering realities must now align with the bureaucratic implementation of CADA. Growth is currently paralyzed by permitting and grid connection timelines that can exceed 10 years. Accelerating this timeline requires a policy shift toward proactive regional zoning. This involves pre-mapping geographic areas with existing grid capacity for fast-track permitting. The connection queue itself must be reformed. The current first-arrived, first-served model clogs the system with speculative projects. Moving to a first-ready, first-mature framework will prioritize optimized facilities and clear the queue of unviable projects. Digital sovereignty is a physical engineering challenge. It requires building AI infrastructure as a symbiotic part of the electrical grid.